This simulation represents the tension in mobile development. One side prioritizes the precise, high-performance rendering of native XML layouts, while the other leans on the rapid prototyping of cross-platform web wrappers. This split-screen mockup highlights an application called My Store. On the left, it displays the visual hallmarks of a Tailwind CSS and DaisyUI web app, complete with rounded utility cards, tight flex-like layouts, and variant-based styling. There is no web view rendering this interface. It is not a React Native wrapper bridging JavaScript to the OS. The codebase on the right is written entirely in BASIC for Android, or B4X. It compiles directly to native Java and Android bytecode. The application creates a highly convincing visual illusion. When you look at the interface, you see standard web components. When the device processor executes the code, it is rendering native Android widgets. This is achieved by combining a custom component library called B4XDaisyUIKit with a strict single-activity routing framework. This architecture allows developers to write imperative mobile code using the same utility class UI construction used in modern web development. By fusing these two approaches, the development process removes the step of traditional layout design. You write code with the ergonomics of the web, but deploy an application with native execution speeds. Traditional Android development relies heavily on XML layout files. These are decoupled markup documents that define the UI structure, which the system must parse, inflate, and attach to view objects at runtime. This separation of concerns creates maintenance friction. When a developer wants to build modular, responsive interfaces that react instantly to user state changes, they have to constantly jump between the business logic layer and static markup files. The B4XDaisyUIKit replaces the XML requirement with a strict property assignment model, where every visual attribute is defined programmatically alongside the application logic. We call this a utility class model. Instead of calculating custom margins and hex codes in a nested XML tree, developers assign simple string modifiers like primary, base 100, or size 10, which the framework maps to native object properties. Writing user interfaces this way means visual state is defined in line with data operations. You construct the view at the exact moment you have the data ready to populate it. Dropping the XML layout system reduces the cognitive load of managing secondary design files. The logic that drives the application and the code that displays it exist in the exact same workspace. This side-by-side comparison shows the exact instantiation of a B4XDaisy card object. The visual output on the left is entirely generated by the 12 lines of code on the right. Rather than defining complex shadow depths or corner radiuses, the developer assigns simple string parameters. The size is MD, the style is border, and the background color variant is base 100. Under the hood, the toolkit catches these strings and translates them into native rendering commands, applying the elevation shadows, padding limits, and color themes required by the Android operating system. This programmatic approach extends to the global navigation structures. The top navbar and bottom dock are instantiated and positioned dynamically through the B4X page resize event subroutine. Calculating the scrollable content area becomes a simple mathematical operation. The view takes the total screen height and subtracts the height variables of the navbar and the dock, allocating whatever vertical pixels remain to the product catalog. Because the resize logic relies on dynamic subtraction, the layout automatically adjusts to fit any screen size, from a compact phone to a large tablet. Treating the UI as an array of programmatic objects rather than a static markup tree makes the entire visual layer malleable. Components can be injected, removed, or restyled at runtime without a performance penalty. One heavy task in mobile UI is translating raw database arrays into scrollable visual lists. The My Store app handles this inside the List Create Row Content logic block. As the list control asks for new rows, it passes the raw data map directly to this subroutine. Using the data provided by that mock database map, the routine generates a new native B4Daisy avatar, sets its image path, rounds its corners, and sizes it using the utility string size 10. Before it builds that product row, the code checks the data map for a Boolean flag called header. If that flag is true, it skips the avatar and instead generates a text view, dynamically altering the row's structure on a per-item basis. Keeping the view generation process inside the same class module where the data is fetched creates a direct execution path. There are no intermediary classes slowing down the render pipeline. This tight coupling of data maps to programmatic view generation avoids the architectural bloat typically associated with building nested recycler view adapters in standard Android development. Native UI speeds are hindered if navigating between screens resets the application state. In traditional Android development, moving from one activity to another triggers OS lifecycle events that often destroy global context. This 3D diagram shows the B4X main page single activity router. The wide baseplate is the persistent root view. Global overlay is attached directly here, safe from lifecycle destruction. Middle layer pages slide in and out of the central viewing area via the M stack of page IDs array. When a user leaves the product catalog to view an item detail, the router does not destroy the catalog page. It simply removes it from the immediate view hierarchy, keeping its scroll position perfectly intact in the background. Because the global overlays sit above this lateral page swapping, they operate independently of the navigation stack. An alert triggered on the home page will continue displaying even if the target view shifts underneath it. Operating entirely inside a single stable activity is what makes seamless, web-style navigation possible inside a compiled Android environment. We can track the execution path of this architecture when a user taps a product card to open the detail page. The tap event triggers the Show Page with Loader subroutine directly inside the B4X main page router. The router first commands the global app loader to make itself visible on the root parent layout. The code then hits a 150 millisecond sleep function. This briefly yields the main thread, giving the native Android UI pipeline time to render the global loading canvas to the screen before the page generation begins. Once the thread resumes, the router tells the B4X Pages Manager to show the target product detail page, pushing it to the navigation stack. Finally, it commands the global loader to hide. By orchestrating transitions through a central router, the application's state stability is maintained. Feedback loops like loaders and toasts transcend individual page logic, allowing for a consistent user experience. High-level abstractions are frequently criticized for trapping developers. A framework that makes UI fast can sometimes restrict access to the hardware features provided by the operating system. We can test this by looking at a specific OS-level feature, asking the Android launcher to pin a shortcut to the home screen. This code snippet shows how the framework handles the requirement. The standard B4A code pauses, giving way to an injected block of pure Java text. Inside this exact injection, the code directly accesses the native Android shortcut manager. The basic logic then utilizes Java Object Reflection to bridge the gap, triggering the static Java method as a native API call. Supplying a native escape hatch within the same text file ensures the framework can scale to complex requirements. The abstraction speeds up the visual design, but steps out of the way when hardware integration is necessary. This sequence visualizes the application's 3 layers. The solid base represents the hardware layer. On top is the state layer, the B4X main page router, managing global context. Finally, the UI layer completes the assembly, translating string commands into native visual elements. By separating these concerns, the visual code doesn't have to manage the memory implications of navigation or device hardware constraints. Combining these 3 layers removes the requirement for static XML markup files and reduces the complexity of juggling multiple Android activities. The architecture driving My Store illustrates that native performance and the rapid ergonomics of modern web frameworks can exist within the same compiled codebase.